So we're talking about fluid mechanics, which means statics, and dynamics, and a very important topic in fluid mechanics or in lots of engineering subjects or in life in general is conservation of energy. So let's talk about conservation of energy, which we know energy cannot be created or destroyed. It can only change form. But let's look at conservation of energy considering fluids from the standpoint of fluids. So I'm going to take a little fluid over here. And here is a fluid, and I am going to represent it by this little square, and I'm going to say it has unit mass M. So if it has unit mass M, then gravity can act upon that unit. So then when gravity acts upon the unit of mass M, then that's a force. That's a force due to gravity that we're used to talking about. So there's definitely going to be a force due to gravity acting upon the center of this mass. Force due to gravity equals the mass times the acceleration due to gravity, as always. And for this piece of mass, all of its energy has to be constant if it is moving with no, oh, and this is volume, by the way, so it's actually three-dimensional because it has a mass. No acceleration. If it has no acceleration, it can have velocity is constant. It can be moving, but it has to be constant. It cannot be moving with a velocity that is changing over time. It has to be moving with constant velocity or standing still. Then this little small unit of volume has pressure acting upon it from the other units of volume that are around it. This unit of volume is also sitting h, height h, away from the ground. So it is elevated by the other units of volume around it. So we're basically saying, let this be the situation we're talking about. And if this is the situation we're talking about, we can say, therefore, the conservation of energy equation as it applies to this volume of mass can be written as follows. Now we can write the conservation of energy equation for anything. It just says that the total energy equals constant. There's no change in energy. Lots of different ways to write that. We can say energy in equals energy out. We can say energy in, we can move energy out to the other side of the equation, minus energy out is 0. So it is there is no change in energy, but the total energy in this equation has to be the total energy. The total energy never changes. So that's how it was said here. Total energy, or the sum of all the energies, equals the energy total. So here we go. In terms of this equation, we say that total energy is the sum of all of these energies. And what the point is here is that as kinetic energy gets more, then E total does not get more. E total does not get more. As kinetic energy increases, then the energy due to potential must have decreased or something like that. So this must have decreased, or this decreased, etc. So it's saying that total, this all has to sum the total. Now let's look at the different energies that are acting upon this. With a basic knowledge of mechanical engineering, we remember that there is an energy in the form of any mass that is elevated. The energy in the form of any mass that is elevated is called potential energy. And that potential energy term is always relative to the mass that has that potential, the height that potential is from the ground, that's h, the mass that it is, and then acceleration due to gravity, which is 9.81 meters per second squared here on Earth. Then we know that an object that is moving, and we're saying this is moving at a constant velocity. So if this mass is moving at a constant velocity, then we also know kinetic energy is the energy inherent in the motion of an object. It is the energy that can do work on an object by, for example, moving that object over a distance. And that the amount of energy that it has, which is measured in joules, just like potential energy is measured in joules, is the more mass there is, the more energy it has. So mass is in the numerator. The more velocity it has, that's effect squared to the amount of energy that it has. And then it's all divided by 1/2. So we're not deriving this equation today, but the equation for kinetic energy is 1/2 mv squared. And then what we know about our what we need to know about fluids is new. So we have probably explored the concepts before about potential energy and kinetic energy, but the energy due to pressure, well, that's a new one. And it's described as the amount of um, mass, depending on the amount of mass, it's going to uh, exhibit a pressure for a given weight density. So this equation is new. The energy due to the pressure that this can exhibit, because you can see that other masses are exhibiting pressure on it. So it is exhibiting an equal but opposite pressure on the other masses around it. And the energy to do it from that pressure is directly proportional to its mass. It is, of course, scaled by acceleration due to gravity. So it's the force of gravity that it has. It's pulling down at this force due to gravity, and times pressure over the weight density. So that's our new equation for the amount of energy potential it has because of the pressure that it is making due to its mass, pulling it down here. So if we add up all of these, then we have mgh plus 1/2 mv squared plus mg pressure over weight density. And then what I did is I ignored the fact that there is a volume in the denominator. But if we can observe this and we think about what mass in every term means, I have a mass here. I have a mass here. I have a mass here. I have 1, 2, 3 terms in my energy equation. It's all the same mass. It's M1. So it's just that fluid of unit mass M. And I know from a fluid's perspective that one of the characteristics of a fluid, or a material property of a fluid, is mass density. Mass density is equal to the mass times a unit for any given unit volume of a fluid. That's a material property. For water, density of water, it's 1,000. And this is in kilograms per meters cubed. So we look at this little tiny volume. Here's my volume V. I like to put these little, these little hats on V so that they differ from velocity, because velocity is written like this. Velocity is a small v, usually with always with a vector over top because it has scale and direction. Velocity. But then when we are talking about some topics in engineering, definitely in fluids, we're often talking about volume and velocity at the same time. So I like to make volume look a little different with these hats on here. This is not an everybody thing, but this is a me thing. And then that just kind of keeps me straight. Here we go. This is volume. And where velocity is meters per second, distance over time, volume is in meters cubed. So here's my meters cubed of volume down here. And it just means how heavy is this block? Water is pretty heavy compared to air. Water is pretty heavy block. So mass is pretty high for that volume of meters cubed. Air is pretty light, so mass would be pretty low, so density would be low. The salt water, the density of salt water is something like 10, 20 kilograms per meters cubed, something like that. So that just means with the salt inside that water, it's actually heavier. So what that is a material property. When I look at this equation here with mass in it, it's like a function of the current problem, right? It's a function of the current problem. But if I can look at that in terms of density, now E total is a function of material, of the type of fluid. If we know the fluid, then we would know density. We would know density. We would know density. And all we have to know is height, velocity, pressure. Yes, because we know density. We know the fluid. And in most cases, we know the fluid. So when I see mass up there and I'm doing fluid mechanics, I say, wow, I want to divide by volume. Because I don't really like mass by itself. I like working with density. I can look it up in the back of a textbook or online, which has replaced the back of the textbook. I can look this up in tables, find out what is the density of the fluid I'm working with. Long story short, I'm going to divide by volume. Divide by volume, divide by volume, so that I can group this mass over volume, mass over volume, mass over volume. All that is mass density. So there we go with mass density in this equation, mass density in this equation. So the total energy that is going to be inherent in this fluid of unit mass is going to be the sum of the potential kinetic and energy due to pressure because of its mass. And as those change, as the velocity changes, as the height changes, etc., then I mean the mass cannot change. But as those change, the sum has to equal the total.